Hello and welcome back to the Hyperthesis podcast, episode 55. Two nice numbers. And today we're going to be talking a bit about quasiparticles. My name is Pheely.
I'm Patrick.
I'm Leah, and 55 is one number.
Oh, there are two numbers combined.
I know, I'm
two digits.
I'm just messing with you, don't worry.
Anyways, it depends on perspective. Who knows, right? There's infinitely many ways to add things to make 55. Anyways, so to start off today, we're going to be talking a little bit of the quasiparticles. So whatever that means for people. So to start up, I want to start with this kind of like a news-ish, because I think this article was published yesterday about what they found on the quantum entanglement wave, which sounds weird, isn't it? Because normally we think of quantum entanglement as, let's say, two particles get entangled and they kind of stick together quantum mechanically and do strange things. But what is quantum entanglement wave? So imagine those quantum entanglement or quantum entangled particle moving and as like a wave. So this one is for triplons. So which is basically a quasi-particle. Quasi is basically like not a real particle, but behave like a real particle.
I think we need to quickly say what entanglement normally would be. So two particles are quantum mechanically entangled if they're connected in some way. So if you measure one of them, it affects the other one, what you would measure the other one. In some way, and it's weird because even if you have these two particles separated by many light years, if you measure one particle in its one state, you instantaneously know the state of the other particle very far away. So it's basically like whatever happens to one, the information you learn from that, you know about the other one.
Well, yeah, but the tricky part to make that happen is how do you make it still entangled when it's far away? I think that's one of the challenges, right? So, and to explain a bit of the quasi-particles, normally particles is like, we saw something in nature that behave certain way, we call them particles. And, the things that we know from, let's say, first year physics or high school physics, particles like small things, small mass. And then for quasi-particles are things that not exactly particles. Maybe they are a wave of sound, but in certain situation, it behaves like a particle and it can be described like a particle. So in that sense, we define what we call the quasi-particle to call it like phonons. Is basically wave of sound that behave like, or like not vibration, the sound wave that behave like particle when it go through the material. So quasi-particle is basically anything that can be expressed or described like a particle, if I got that right. So this place for triplon is basically a quasi-particle describing a triplet state of a material or of particles of substance, basically. So it's really tricky or hard to make and really difficult to observe experimentally. So researchers usually do this type of tests or experiments on macroscopic material instead of quantum materials. So basically, instead of going like really cold, like ultra cold or really small to have quantum effects, they do in terms of like molecules and like the chemistry level of scale, so that they can observe something that's similar or close to the quantum effect. So in this case, these quantum materials that was designed, so they decide to create the phenomena that's not found in natural compound, that really close to the exotic quantum excitation. So they use these small organic molecules to create artificial quantum material with basically unusual magnetic properties. So this type of cobalt, fluorocyanide molecules basically have two frontier electrons. And when you monitor this type of magnetic excitation in the first molecule and later in the larger structure in the chain of the molecules that they make, they start basically simple from the first molecule, increase the complexity, and see how these excitations travel through the chain of the molecules. So they can demonstrate that this type of singlet triplet excitations in the building block can traverse this kind of molecular network, and it looks like the exotic magnetic quasiparticles that we know as triplons. So basically, they create this kind of exotic quantum magnetic excitation that travel through the material, and they can show that this type of strategy to create that you can emulate basically quantum properties in the microscopic materials that open up this a new realm in the quantum technologies. So if you want some kind of quantum effect or quantum like effect, you don't need to go super quantum. You can create this kind of like small organic compound that imitate this quasi particle behavior that comes from quantum mechanics realm. So I think this pretty exciting news. I don't know too much about it, but here it is.
Yeah, I got a little lost of exactly what you said during that. There's just a lot of big scary words being said. So the gist of it is that there's these quantum you can have quantum entanglement, and they detected quantum entanglement waves, which I guess I'm like that's how they stay entangled together is they talk to each other through these quantum entanglement waves, which are quasiparticles, these so-called triplons. And in this material, which you said it doesn't have to be a super quantum material, it can be more macroscopic and bigger. They were able to create something that kind of like mimics these triplon states between,
Yeah.
yeah.
Well, I think well, I haven't read really the full paper of it, but from what I get from the article, basically, it gotta travel somehow, right? Like how phonons have to travel to materials with the sound wave. Instead, these kind of like they use the frontier electrons kind of as as a singlet triplet states uh, that travel to this kind of organic compound as and be described as a quasi particle, like the quantum entangled particles.
Okay, and okay, that makes a little bit of sense to me. I guess we'd have to read the paper fully to get a full explanation.
Hmm. Yeah, a lot of I think quasi particles are excitons, right? Like some kind of excitation in the molecules that travel through the chain of molecules or the network of molecules. I think those are called excitons. Maybe triplons might be part of excitons, or I'm not too sure about that. Well, if anyone is interested, you can basically just look up detection of a quantum entanglement wave using real space measurements. I think the article came out on August 23rd, which at the time recording was yeah, basically yesterday.
Very, very interesting. And I'm curious how big we can go with that in terms of the molecules that can be used. Because, I mean, if we can somehow entangle proteins, very complex chains of molecules, that would be quite fascinating to observe. But of course, these are quasi-particles, so can you make quasi-particles out of proteins and even larger molecules even? Be very interesting
Yeah,
to
like
see.
can you excite certain parts of the protein and make that travel, right? Like, oh, like when I say excite, I mean like excite the electrons to a higher state, and hopefully it would pass on that energy or interact with the next molecule and pass along that thing, or that energy or like the excitations and that move along the chain of the molecules. But who knows? I'm not expert in like experimental method of that. I actually have no idea how someone would do that at all. Like, do you put like a pinprick at the one end and just excite it with heat, or do you use laser or some kind of photon to excite it? I think there are multitudes of ways you can excite an atom. So, but to make it like a triplet or singlet states, I think they're a little more finicky. It might requires like very specific energy level and really precise control.
In other news that came out a bit further, well, it's a slightly older news, but still quite new. I think it was within the month of August, but we have new results from the G-2 experiment, or the muon G-2 experiment, which is taking place at Fermilab. And essentially, what this experiment is intended to demonstrate is a very precise measurement on the magnetic moment of a muon. And so it's able to test it through a very somewhat complex process, but essentially the G in the G-2 stands for gyration. And it's how a muon moves essentially in a magnetic field that's applied externally. And so it has to do with the magnetic moment of the muon and the value of G that's predicted by the current standard model, which is largely accepted as how the universe works, at least for most of the forces. This value of G is just slightly larger than 2. So when we do G-2, we get a number that's not 0. And we have very accurate predictions for this number. However, based on results from first Brookhaven National Laboratory, and even before that at CERN, but starting at Brookhaven National Laboratory, and then all that equipment was moved to Fermilab after the experiment ended in 2001, and then continued at Fermilab, we are seeing that that value of G-2 is actually different than what the standard model predicts. Now, this is something that we've known for, or at least had suspicions about for a while, in that the standard model isn't the whole picture of all the particles and how they interact and everything to do with these elementary particles. And this will be one of the pivotal experiments that actually confirms it. Now, they have not confirmed it as of yet. So just recently, as of August 10th, the results from the first 3 runs of this muon G-2 experiment were released, and they were able to give us a value of G-2, which I will not read out, just it's a small number, not incredibly small, but this result is not fully confirmed. So in particle physics, you need a result of what's known as 5 sigma, which means that you have a very high or a very low chance of a random event causing this result, and it's almost definitely true. So for example, the Higgs boson, you needed 5 sigma, and for a lot of particle physics results, you need 5 sigma. However, that takes a lot of time and a lot of tests in this case and runs of the experiment. So we aren't quite at that 5 sigma. I think last I checked it was 4.2 sigma. But given that there are still runs to analyze, it ran for 6 years, and we've only done about half of those runs. In a couple more years, we'll almost definitely get that 5 sigma and see exactly how wrong the standard model is.
Well, a lot of these kind of experiments are statistics, right? Like, so basically, a lot of particle physics right now are looking for rare events. And we say rare events is really rare, right? So if you want to have, let's say 5 sigma, let's say you want a lot of data to prove, to get those, real, supposedly real interactions that happen that you can detect. But then if you detect 3 of them, then like how can you be sure that it's a thing, it's not noise, right? So you're gonna have a lot and lots and lots of data, or like try to collect it over the long time. So even though we kind of getting close, it might be right, like, or it might not be, but it looks like it's going to be somewhat. We are kind of close. And one thing about particle physics, like, yeah, there's a lot of data collection. To me, it's like, well, I think astronomy also has a lot of data collection too. I'm excited to see what we gonna get from the muon G thing, because even though it's not directly related to my research at all, or well, actually not at all, but fundamentally, it's really important to have a very precise data, or the understanding of why standard model doesn't work, and with real, substantial proof.
Yeah. The other thing is that, I mean, what people call the standard model is anytime we realize there's some kind of something wrong with our theory, we correct it and then we add it on to the standard model. So it's like the standard model is in quote unquote always correct. But we don't, again, I say this all the time, but we don't have a full theory of quantum gravity, right? Like quantum mechanics and gravity don't work together. So we know that the standard model's wrong in some sense, but this is one of those first times that it would be wrong in terms of quantum electrodynamics, I think, because you can calculate this 2G factor stuff with QED and you can get it really high precision. You do these Feynman diagrams and you do these higher order calculations. And I think it would be the first time that, quantum electrodynamics, which is our best theory ever, is just kind of wrong on its own. Maybe I'm wrong there. I don't actually know, but we know QED is really, really, really good. And if the QED calculations don't match the experiment, then QED is off in some sense. Which again, we already kind of know, but this is
Well, I remember when I was taking I think when we were taking the particle course, one of the website we visit was the particle data group, the PDG. And there was like all these results from experiment. I think the whole section on violations. So basically, the results that violate the standard model. So it depends on what you mean by wrong. I would say like, yeah, they're always wrong. All these violations happen all the time. But maybe it's quite rare, but it does happen all the time. Am I wrong?
I mean, we're trying to figure out if it happens more and more. So the standard model is widely accepted, and experiments like the muon G-2 experiment are showing that it is in fact wrong. And of course, we've had suspicions. But even in our undergraduate, I was working for my honors thesis on trying to detect violations. And while that experiment, which was the Babar experiment, didn't show any proof of what was known as charged lepton flavor violation. There's a new experiment called Bell2, which is based in Japan, which is also trying to essentially find instances where the standard model is not true. And in that case, it's looking at where two different leptons are produced, where normally two of the same leptons are produced, which leptons are just electrons or muons or tau. So it's a very interesting, and I highly recommend anyone who's interested to go take a look at both the logistics and the statistics behind this whole experiment, especially trying to move the rings in which the giant, essentially containing superconducting magnet that originally start in Brookhaven, which I believe is in New York, and how they got it to its current place in Fermilab, which is in Illinois, close to Chicago, and involved like a 5,000-kilometer journey over 35 days where they essentially took it out by boat, took it all the way around the east coast of the U.S., up the Mississippi, and then trucked it in. It's a whole logistical thing, but it's also a cool story.
All right. I think it's time for us to move on to the main topic on quasiparticles. So I'm going to pass the torch on to Liam to talk about quasiparticles.
Yeah, so you already talked about these triplon things, which I'd never heard of until today, and maybe excitons, which also I don't never heard of until today. Which is kind of one of these. It goes to show that there's a lot of different types of quasi-particles out there. There are very, very many different kinds. So today I'm going to talk about some of the more basic kinds a little bit and kind of describe what they are. And quasi-particles, they've come up a bunch before actually in our previous episodes. We might have just not called them quasi-particles. And they're really important. Pheely talked about them a little bit already, and they're actually responsible for why our computers work and why we can record this podcast right now. So in episode 46, Patrick, I believe, told us a bunch about semiconductors and transistors and all that good stuff, very important things in our world, how they work, and how they were one of the most important inventions of all time. And Patrick briefly explained how in semiconductors you have two different regions. You have what's called an N-type region and a P-type region. He can maybe explain it better than I can, but I'll try. And in this N-type region, there's an excess. This is like a very go listen to episode 46. That's the best thing you can do. But here's my very short explanation: is that in these N-type regions, so imagine you have like a block of material. In the N-type region, there's an excess of electrons. So there's some free electrons that can kind of move around between the atoms that make up the block. And in the P-type region, there's actually a deficit of electron, which leaves these kind of empty holes where electrons would normally be. And so what happens is that the electrons jump between these holes, and what you see is that actually you can effectively describe this as if the hole is a particle itself and kind of moves around in the P-type region.
Well, I think one thing I could kind of like example, if you heard of the phantom jam for traffic, right? So basically, like it stops and starts. It's basically like a hole. A hole happens in traffic, and this part is condensed, part is not as condensed. If you look at from the bird eye view, but if I'm tracking the hole or the part is not condensed, it appears like it's moving backwards or something like that, right? Or you could track the part that's like really jammed, and that part also move like a. You can describe it almost like a particle or some kind of wave, right?
Maybe you can like imagine you have like a bubble underwater, like in the ocean. There's nothing there; it's just a lack of water. But the bubble kind of moves as if it's a single object, like a particle. That's kind of what's happening in these p-type regions of the semiconductors. Is that normally where an electron would be, there's nothing, but the whole kind of moves around like this little bubble. Um, and so exactly, these holes behave and can be modeled exactly as if they're a particle. They have an effective mass, which is the same as an electron's mass, and they act like they carry a fundamental positive charge that's opposite to the electrons. So in general, not just for this example I gave, but these quasiparticles, they're emergent from behavior of particular configurations of matter, and they allow us to take a system that's with a bunch of very complicated microscopic interactions and model it as though it was the kind of a single, more simply interacting particle, like this hole in your semiconductor. And I'm not going to talk about semiconductors anymore. That was just a very common example because without semiconductors, your computer doesn't work because your transistors don't work. So go listen to episode 46 if you're interested in that. So that was kind of maybe hard to argue what's the most important thing in physics, but that's a very important example of a quasiparticle. And the reason why quasiparticles are nice, as far as I'm concerned, well, for many reasons, but they're way easier to model and describe mathematically. So you can take a very very large amount, like an Avogadro's number amount of interacting particles, and treat them as like a single object, and that really simplifies your calculations and your math. I actually do this kind of stuff all the time, but not with Avogadro's numbers of particles, maybe a smaller amount. And because of the nature of my research, when I think of quasiparticles, I don't think of holes in semiconductors. I think of quasiparticles which are formed with the collective excitations of many different constituent real particles. So when I say real particle opposed to quasiparticle, I mean something that's physical. Like if I took this hunk of semiconductor and I kind of melted it down and I picked it apart piece by piece, there's no holes. The whole particle isn't a thing. It's just a lack of a thing. But the electrons are real. So the electrons are kind of fundamental physical particles, but the holes they're not there. They're just something that's kind of we treat as real. The example I think about the most for quasiparticles has to do with sound waves, which Pheely you talked about already, actually. Phonons, not to be confused with photons. Photons are particles of light or particles of electromagnetic waves, whereas phonons can be thought of as particles of sound. And we've talked about them before, and you talked about them earlier, but they can be thought of as density waves. So we've done an episode on everything. We did an episode on sound as well, and kind of music and all kinds of stuff like that. But when I hear something, so if you talk to me and the sound enters my ear, what I'm hearing is that someone's voice, their vocal cords vibrate, it causes these kind of different regions of density in the air, these density waves, and the density waves travel into my ear and they fire off a signal, and then my brain does something with it and it makes a sound.
Well, I think the sound is actually really similar to the phantom traffic jam, right? Because it's not like the water wave or mechanical wave. Like water waves, like the molecules of the water goes up and down, but the wave traverse the perpendicular to that. But sound wave is basically compressed. Well, the air got compressed in the same direction as it travels. So in a way, it looks, if you look at the molecules of the air, it looks like it got compressed and decompressed, and that decompression move along the air. It's like how traffic jam, the phantom jam work, right? And so you can model that as like a particle, or like, this blob of compression and decompression, a couple together that move into your ear. And I think that's the beautiful thing about quasiparticle, right? Even though we know for sure this wave, but they have this equivalent behavior that we can describe using particles. And phonons are very useful in modeling materials, see the properties of material, or try to figure out how light propagate to, not just light, the magnetic field propagate to materials, semiconductors, how it works, phonons used to determine the band gap, and all this stuff.
Yeah, phonons are super important in condensed matter physics. And often you model these sound waves or these excitations through some material. So imagine that you're like studying a superconductor, which is, maybe it's a bit more of an extreme example, but you need to take into account the fact that there's all these sound waves moving through these phonons. And how they interact with each other and how they interact with other things, and they're super important essentially. And the difference between like regular sound waves in the air and phonons is that phonons can move. They have longitudinal, or what are called longitudinal modes, so like a longitudinal component, but they can also have transverse modes. So they can behave like, a sine wave, but they can also behave like these density waves, or this kind of like this traffic jam wave that you talked about. Yeah, so in these condensed matter systems, these solids, these sound waves will often form due to thermal vibrations or some other outside external force. And they travel as these small particle-like density excitations, which obeys physics that's very much. It obeys physics that's exactly that would describe a regular particle in some other system, and that's why they're quasiparticles. So one example is a simple crystal, which is simple crystals are made up of these periodically repeating lattices of atoms, which are all very tightly bound together since they form a solid. So, you think of your three states: solid, gas, liquid. Gases bounce around and whiz everywhere. Liquids do that, but they interact a bit more, so they kind of slosh around. And solids are all rigidly kind of interlocked next to their neighbors, and they don't move very much, but they do vibrate a little bit. They jiggle. And due to these thermal vibrations that these atoms have, or any other external stimuli which cause vibrations, many of these phonons can form and they can travel through the crystal. And although I study gases, ultra cold gases, not solid crystals, the phonons are exactly what I study as well. These quasiparticles in the gas, and they play such a major role in these physical properties of condensed matter systems. Like they affect your thermal conductivity, your electrical conductivity, and they show up in all these other different branches of physics. So phonons and holes are very important quasiparticles that many people have heard of in physics, at least.
Well, I want to clarify that normal sounds that we hear are not phonons. Phonons are very elusive. So you find in like crystals and certain crystal and such, so that like basically they are small vibrational modes that travel through, right? They're not just sound wave that we hear, because sound wave that we hear in our daily life doesn't behave like particles. They just behave like waves. But if you go deep enough or in the quantum level, those quote unquote sound, basically these tiny vibrations that traverse through the material, behave sometimes like particles if you set up things correctly. And a lot of things, excitations of molecules would create those vibration modes or vibration that travel through the material. That's why it's so important to recognize the effect of phonons, because a lot of interaction create small vibration modes or small vibrations to travel to the material.
Yeah, that's something that's always confused me a little bit because I guess if like you think of light coming out of the sun, right? You can treat it as just electromagnetic waves. Um, but you can also treat it as many, 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 many photons. So the quanta of light, the kind of like these discrete chunks of light, all kind of interacting together. So why is it that when you have sound waves coming at you and hitting you, why can't you treat it as many, many, many little phonons together?
Well, I think it's a matter of scale too, right? Well, you can treat light as photons coming into your material, your metal or whatnot. You can treat particles as wave. You can, right? But the
Yeah.
wavelength would be ridiculous. That it doesn't make sense. No, in a way, you probably can treat all sounds or vibration travel as phonons, but
Mm.
in the scale that we talk about for, let's say, for our ear, it doesn't matter. Like particles like your microphone can be thought as waves, but the wave property is so minuscule, like it's almost like non-existent. It doesn't, it's impractical to talk about it at all.
Another argument that I've heard just why sound waves aren't really considered a whole bunch of phonons is that there's not really a ground state. So, for example, if you have like this crystal structure where you have um, the crystals or the individual elements are quite relatively still, and then you have a disturbance. So, say some sort of vibration that then travels throughout the crystal lattice and forms a phonon. You start at some sort of ground state, and then you've excited it. Whereas um, with the air, there's not really like this solid ground state that's then excited and then reduced back to this ground state again. And I believe that's from an actual quantum field theory book, if I remember correctly, that was talking about phonons and essentially how you do need specific conditions for phonons to exist. And in fluids in particular, like just open air, it's not controlled enough for them to
Well,
really exist or to think about them like that.
well, even with photons of light, they don't have a ground state unless you're bound in some system. The energy of a photon is it's proportional to it's proportional to its frequency, right? So you can get these arbitrarily small frequencies. You can never there's no like minimal state. It's when you have bound systems, you have ground state, and when you have free systems, you don't have a necessary ground state. You have these continuous energies. So when you describe phonons in solid state systems, they're all periodic. You have this periodic lattice. So in each kind of site, you have a bound state, and then you just infinitely repeat them. So it makes sense to talk about bound states there. And similar, if you have light trapped in a cavity and stuff like that, you have, think of like a particle in a box kind of thing. But when you have a particle in free space, then you don't have a bound state, and that's also something that confuses me on a deep level that I probably shouldn't get into.
I think that also electromagnetic field is very specific. If you think of Maxwell equation, right, divergence
Yeah.
B is zero, so there is some kind of bound thing.
Okay.
Like is you it's niche because when you think in crystals, like phonons are kind of in crystal because it's kind of like it's bounded in some way, right? But I think electromagnetic fields, when they travel through the vacuum, is also bounded in a sense of the magnetic field. But if you think of sound, mechanical wave that travel through air, it's not exactly bounded.
Yeah, and I also really liked your answer earlier, Feely, with the whole scale thing. I think that's a really intuitive way to think about it. And then the other thing too is that, um, thinking about waves isn't even the best way to think about it. You should think about things as excitations in quantum fields. So a phonon, as far as quantum field theory goes, is that you treat your atoms are described by field operators. and that the phonons are excitations in the ground state or in the vacuum where you have no excitations, and then same with light. Anyway, that's the best way to think about it that we have so far.
So I know phonons aren't the only quasi-particle though, and I bet there are more. So
Yes.
what are some of them, Liam?
I don't want to get into too many of them today, but I have some other ones prepared. Um, the next one I want to talk about, we need to talk about spin first, which is a dangerous topic, because in quantum mechanics, particles have this fundamental property called spin. And this is very much related to this 2G factor we talked about before. Um, and we don't really fully understand what spin is on a deep level. I mean, we know how it works super well, um, but it's related to the angular momentum of a particle. So you can imagine you have like a ball, and you're a basketball player and you spin the ball on your finger. Um, that's the best way we can think about spin, is if a particle's kind of spinning like that about some axis of rotation. Although that's not really true, but we don't really know what it is. It's related to angular momentum. It behaves the same way, but it's this fundamental quantum property that particles have.
Oh, I just want to point out Liam's lie earlier when you said you never heard of exciton until now. I was like, isn't exciton just like excited electron coupled with a hole? Like that's just what it is. Like what you've been talking about, basically just excitons.
Yeah, well, that's the funny thing about quasiparticles, is that people sometimes don't, they have different names and things. So like you can call phonons sound waves, and without realizing that they're a quasiparticle. And I mean, I've never looked up and Googled what is an exciton before, but I guess I've heard of them indirectly.
Well, and also, is it quasi particle or quasi particle? I just like saying quasi.
I I feel like every fifth time I say it, it changes. So I don't
It
know.
sounds cooler. Is it quasi particle? No, quasi particle. I'm just saying.
It depends how I'm speaking. Usually it's quasi for me, but yeah, sometimes I
Quasi
say
feels
quasi.
small and tiny, but quasi, on the other hand, it just sounds nicer.
All right. Well, the next quasi particle is related to spin, and um, we tend to use this, what we call spin, and the axis of rotation about which a ball spins. We kind of use them as the same thing. You can imagine spin as these arrows pointing out of particles about which the particle spins. Although that is a lie, but that's the best kind of intuitive picture we have of it. So imagine you have a lattice of particles, and they all have spins. So, or maybe you have like a 1D line of these particles. So you have a bunch of balls next to each other, and they're all connected with some interactions. You can do various things to interact with these spins. So you can apply magnetic fields, and all the spins will align with the magnetic field. So their axes of rotation will. You can do other things where the spins anti-align, or they do all kinds of weird things. And this quasi-particle is a spin wave that I want to talk about. It's called a magnon. So imagine that you do some weird things to your big line of particles, such that you get this collective grouping of spins that align as this. It's like a wave traveling through the spins where they all align, and then as it passes, they kind of go back to whatever they were doing before.
Well, I have an argument for spin because I think one of the students astutely asked, well, oh, why is it called spin? And if you do quantum mechanics, you realize that spin is basically a type of angular momentum, mathematically, right? So when you
Mhm.
think of angular momentum, you think of, classically, it's like something is moving in a circular way or periodic way. So, well, what do you describe those motions? Like spin. It behaves like angular momentum, right? So we call this spin, even though maybe the particle is not exactly spinning, but mathematically it's kind of behave like the angular momentum. So we just call this thing spin, but it just makes more sense. And when you do right hand rule or left hand rule, we can basically classify spin as you curl your hand, and that's like the way it's quote unquote spins, and you can point your thumb up. And you're like, oh, that's spin up because it looks like it's going like counterclockwise from the top. But even though it's not spinning, so there's like up and down. So this type of spin that we talk about is actually one way to explain angular momentum property of the material.
Yeah, they're so intertwined and directly related. But no one can answer what is spin, though. It's very interesting. But for the sake of time, yeah, if you want to know what a right hand rule is, I mean, you've never taken a physics class, you should Google it. Because I probably would take me 20 minutes to explain what it is. It's not even that complicated. I don't know how to explain it to someone who's never heard of it before. So back to magnons, these quasi-particle or quasi-particles of spin waves. I don't know too much about them, but they seem to be important, and actually, people have won Nobel prizes in that field. So, this is a little history lesson, which is relevant for me, I guess, a little bit. Direct experimental detection of magnons by inelastic neutron scattering in ferrite was achieved in 1957. So we've known about magnons for a very long time now. And the Nobel Prize winner was a Bertram Brockhaus. Who won his Nobel Prize for the development of neutron scattering techniques, some of which were used for this magnon confirmation. And the reason why I bring this up is because Brockhaus was actually a professor, Nobel Prize winner at McMaster University, which is where I go to. Which we have a big neutron scattering department. And since his work, magnons have also been detected in ferromagnets and Ferri magnets or Ferri magnets. I don't know how to pronounce that because I'd never heard of them until now. Maybe we can talk about ferromagnets and other related things another day, and also in anti-ferromagnets. So I encourage people to look into different types of quasiparticles to discuss them and learn about them. And I have one more type of quasiparticle if you guys are interested in hearing about it today. I don't know how we're doing for time, but I want to talk about this one because it's related to my supervisor a little bit. So this last type I want to talk about are called rotons. So the name roton is historical. Physicists originally thought that in superfluid helium, you can spin it, and what happens is that you get these quantized vortices, which we've mentioned once or twice before. So they're little vortices, you can imagine like a whirlpool in a bathtub, that can form in superfluid helium, which is this ultra cold fluid of helium. And people thought that rotons were these quantized vortices were quasiparticles called rotons. But this turns out not to be the case, and even today there's still confusion about that. So there's this really good PBS Spacetime video about quasiparticles, which I highly recommend watching. I love PBS Spacetime; they're my favorite. But even in this video, they actually get the description of rotons wrong, which is interesting. This is one of the first times I've seen them make a mistake. But that being said, quantized vortices do indeed exist. They're just not rotons. So rotons are simply a fancier version of phonons, these sound waves we talked about already. They're phonons. They're these excitations in a gas, in a Bose-Einstein condensate specifically, or even in superfluid helium. Actually, specifically, rotons were first discovered in the context of superfluid helium. So they're the excitations in it. They're phonons. They're these sound waves. But they obey a different dispersion relationship, which is just a fancy way of saying that their energy actually depends on their momentum in a funny way that we're not used to. So there's the speed of these rotons can do weird things that normal phonons cannot do. So for example, rotons have what's called a roton minimum, which is a local minimum in the dispersion relationship. So it's like this, this parabolic dip in its dispersion. And what that means is that these quasiparticles, they can have a finite momentum, but a zero velocity, which is kind of weird to think about. So this was first theoretically and experimentally discovered in liquid helium, which is a very strongly interacting liquid. However, it was rotons can also be found in Bose-Einstein condensates that have long-range dipolar interactions. And Bose-Einstein condensates are what I study, and we've talked about them before a bunch. And this is what my supervisor, I don't want to say is famous for, but in the BEC community, this is what my supervisor, Duncan Odell, is famous for. Was he showed that, along with his colleagues back in 2003, he found that if you radiate a Bose-Einstein condensate by an off-resonance laser, the BEC develops these long-range dipolar interactions, which is just a fancy way of saying that instead of just contact interactions between the particles, there's longer range ones, like in a plasma, which is what we talked about previously as well. And that by tuning the laser intensity and the frequency, you could produce rotons in this Bose-Einstein condensate and get a roton minimum just like you do in superfluid helium, which is kind of interesting for various reasons. But one of them is that superfluid helium is super strongly interacting, and BECs, Bose-Einstein condensates, are very weakly interacting typically. So, I have to get in my McMaster Nobel Prize shout out and my supervisor shout out when I can. So those are some interesting types of quasiparticles you may or may not have heard of, and there's many other types, which we even at the beginning of this episode, there was 2 that were mentioned, and I'm sure we'll talk about more in the future. There's like, even if you just Google and go on Wiki, look at quasiparticles, there's so many there, and I haven't even heard of many of them before, so they're very important in physics and our description of the universe.
Yeah, I think the word quasi just means like, seemingly, right? Like
Mhm.
things that seemingly like like a particle. So we just describe similar to a particle. And because particles like so limited, if you look at standard models, there's not that many particles around. There are a lot of materials and a lot of things around. So if you can describe, like we know how to describe particles really well, right? Like and wave really well. So things that behave like a particle, we can find a description that intuitive to us. So that is a good thing, I guess.
I think when you look at the standard model, there's a lot of particles actually, but I think a lot of them are very short-lived, so we don't see them much. But yeah, I agree
Well,
with you.
depends on what you mean by a lot, right? To me, like 100 would not be a lot, right? Compared to how many phenomena we have in the world that could be described, right? That's why they call elementary particles, because so few of them can describe a lot of things. And yeah, so anyways, for the interest of time, we should in our discussion here. If you have any comments, just or final lasting comments, just let me know. But before we get into the story today from Patrick, we're gonna get him to tell us how to reach us and how to contact us.
Right. So if you do have comments about quasiparticles, whether you are strongly opinionated about them in some way, you can reach us through a few different methods. The first being our email. So we are hyperthesispodcast@gmail.com. We are constantly checking it just in case. And we are always happy to have people email us and suggest topics, suggest arguments for topics if you would like, whether your favorite quasiparticle is the roton or the phonon or whatever other particle it might be. You can also reach out to us on Instagram. We are at the Hyperthesis, where we post updates about when we have each episode go live, as well as some other updates. You also get to kind of delve into the lives of our guests a little bit, and you can reach us there too. So send us a DM if you have questions or comments, or if you would like to be a guest on our show, like last week's guest. So we are always looking for guests. So if you are an expert in your area, we would love to have you on the show to talk with you about what you study or what you research or what you're really into. You can also find us on YouTube. We are, again, Hyperthesis Podcast. If you just put that into the search bar, you will be able to find us. We have almost all of our episodes up there, if not all of them. So we're pretty caught up to it. So feel free to subscribe, leave a like, leave a comment, and you can also reach out to us over YouTube, I believe. Now, if you are listening to this podcast, great job, you found us. However, if you would like to share us, we are on pretty much every podcasting service available, whether it's Apple Podcast, Google Podcast, Audible. We are based out of Spotify, and again, pretty much wherever we have, wherever can host a podcast, we are almost definitely on there. And also, while you're on there, especially for things like Apple Podcast, feel free to give us a review. We are more than happy to receive feedback for how we're doing or what types of topics you would like to hear. So reach out to us, listen to us, share us, do whatever you can to spread the word about us. And again, if you are interested in being a guest on the show, reach out to us and let us know. So for the story today, we were talking a lot about quasiparticles. And they are really part of a larger field relating to quantum mechanics and density functional theory and statistical mechanics, and a pioneer in many of those fields, and even the discoverer of some of them, is Lev Landau, who was a Soviet theoretical physicist. Now, Landau, before he grew in his mathematical ways and theoretical ways, started life on the 22nd of January, 1908 in Baku, which was an area of the Russian Empire at the time and is now modern-day Azerbaijan. Now, his father was an engineer, and his mother was a doctor.
I think you're gonna say this eventually, but I want to comment on every physicist out there will have heard of this guy for his textbooks. I know you're gonna talk about that, but I just want to say this is the same Landau for you bunch who know of the Landau and Lifshitz series of life universe changing textbooks. Okay, continue.
And
Oh, wait.
also, those textbooks are not for amateurs too. They're like there are people who want to be theoretical physicists and already know the basic or like the advanced levels, and they want to be more mathematical and such. Even like for graduate school is a little bit too difficult.
Yeah, it's weird. Every field of physics has a Landau and Lifshitz textbook. It's kind of funny, actually. There's like a fluid mechanics one, a quantum one. There's a bunch of them.
Well, we will get into those textbooks soon, but he did start his life off with very educated parents, which led well for him. And it's apparent, along with his natural abilities, that he excelled in mathematics. He was able to learn differential calculus by the age of 12, and just a year later, knew integral calculus. For those of you that are listening to this, Liam is shrugging. I'm pretty sure this is like the fourth or fifth theoretical physicist that we've talked about that's learned calculus before the age of like 14.
Man knew calculus before I could like read, probably. Jeez.
Yeah, so he was very naturally gifted and had very good influences from his educated parents. And he was able to graduate at the equivalent of what is a secondary school or high school in 1920 at the age of 12. At the age of 12 or 13. So his parents thought him too young to actually start university at that time, so he waited a year. Meanwhile, he was still studying at a technical institute before he was able to enter the Baku State University at the age of 14. There, he started studying mathematics, physics, and chemistry, but would go on to eventually drop the chemistry aspect of his studies. But he was still very interested in chemistry, as he expressed later in life with some of his theories. Now, in 1924, mind you, this was at the age of 16, Landau moved to the center of Soviet physics at the time, which was in Leningrad. And particularly, the Leningrad State University had a phenomenal physics program. There he studied theoretical physics and received his diploma in 1927 at the age of 19. So that's about the equivalent of a bachelor's degree, or slightly higher. Now, again, at the age of 19, he enrolled at the Leningrad Physico-Technical University, where he would eventually receive a doctoral degree in physical and mathematical sciences in 1934. So again, at the age of 19, he was in his doctorate program. Now, during his degree, he worked in several countries with some well-known contemporary physicists. These names included Niels Bohr, so he went to Copenhagen. Previously, he had gone to Germany and Göttingen and Leipzig, but Niels Bohr is a very notable person who he worked with in Copenhagen in Denmark, and he was at the Niels Bohr's Institute for Theoretical Physics. He was a pupil of Bohr and always considered himself a pupil of Bohr and highly influenced by Bohr. However, after Copenhagen, Landau continued on to Cambridge, where he worked with Dirac, and his final stop was in Zurich, where he studied under Pauli before returning to Leningrad. So he had some pretty big names that he worked with and was a student of. At this point, he was fluent in German and French, along with being able to speak English and Danish and, of course, Russian. Now, after returning from his travels, Landau became the head of the Department of Theoretical Physics at the National Scientific Center Kharkiv Institute for Physics and Technology, which is quite the name. And mind you, he still hadn't graduated with his PhD yet, so he was already the head of the department. Again, brilliant theoretical physicist. There he was able to lecture in Kharkiv, which is now currently in Ukraine, where he and several colleagues wrote a 10-volume course on theoretical physics. And so Liam mentioned them earlier. That is Landau and Lifshitz, who were able to make this course, which is still used by grad students today. Now, also, just before I forget, I will mention that later on he did develop an entrance exam into one of the institutes in which he was the head of. And this entrance exam was so hard for theoretical physics that only 43 people passed it in the decades in which the exam was instituted. So, yeah, pretty phenomenal guy, but I would hate to be in one of his classes, probably.
One of those profs.
Yeah. Now, along with writing this 10-volume course on theoretical physics, at one point he was also arrested. He did try to flee to Moscow, but in 1938 he was arrested due to a leaflet comparing Stalinism at the time to German Nazism and Italian fascism. So he was not necessarily for the fascist movements, no matter what the propaganda said. Now, just 1 year prior, he had taken the role as the head of the theoretical division at the Institute for Physical Problems, which was a part of the Russian Academy of Sciences. So again, very big place for Russia, or in this case, the Soviet Union. And he had also married that same year in 1937. And apparently he was a fan of sharing the love, or polyamory. So he taught his students to have free love. However, his wife was not a fan of this. Now, he was released from prison 1 year later in 1939 after letters from Nobel laureate Peter Kapitsa, and Niels Bohr, who wrote letters directly to Joseph Stalin, encouraging his release and saying that he was a remarkable man.
I heard a story from one of my Russian profs that Pizza actually went in and stole him out of the prison. Like he did a prison escape with them. But maybe that was just my Russian prof messing with me.
I don't know the validity of that, but Kapitsa was certainly influential in his release, whether it was a breakout or a very well-written letter.
Well, it's maybe the source is trust me, bro.
Yeah, trust me, dude.
Anyway, after his release from prison, Landau went on to develop theories for superfluidity using phonons, which we talked about earlier, and also introduced the roton for this superfluidity to function. He was also part of the Soviet equivalent of the Manhattan Project, where they worked on nuclear bombs, and he was tasked with working on the theoretical yields for thermonuclear devices. Other achievements from him include the development of the density functional method, which Liam is very well versed in.
No.
Also, the quantum theory of dimagnetism, second-order phase transitions, and many, many, many more theoretical successes. And with very good reason for his work on superfluidity, he received the 1962 Nobel Prize. Now, before receiving that Nobel Prize in 1962, earlier that year, he had actually been in a car collision where his car collided with a truck, leaving him severely injured and in a coma for 2 months. Upon exiting the coma, he was unable to continue his incredible scientific career. He just didn't have that spark, or something was not okay, and he wasn't able to keep doing what he had been doing for so many years. And he actually could not accept the Nobel Prize in person due to his injuries. Now, Landau died at the age of 60 on April 1st, 1968, from complications due to his injuries, which had happened 6 years prior. Well, Landau did meet an unfortunate decline. Everything from his theories to his textbooks survive, as Liam has said, and as I'm sure some grad student listening to this knows the pain of going through those textbooks. But his legacy lives on in many different theories and names. Many things are named after Landau, and there are also many institutes named after him as well, including one that was developed pretty much immediately after his death. He truly was a prodigy that carried on that intelligence and motivation throughout many years. And because of that, we're able to understand our world much better at both micro and macro scales.
All right, thank you, Patrick, for the story on one of the greatest of all time scientists. So, and that marks out the end of the episode. I will talk to you guys next week. Take care.
Bye, everyone.
See ya.